Hello, everyone. Welcome to the last Young-HOM before New Year. Today we have Sonja Farr, who's going to talk about geometric GRT actions and Deligne's conjecture on Hochschild cochains.
Thank you for the introduction, and thank you to the organizers for having me. So yes, I'm going to talk about, I think, something that's not widely known, which is GRT, the Grothendieck-Teichmüller group. This is part of my PhD project. This is basically what I've been working on the past 1.5 years or so. So because it's not widely known what this is all about, I'm going to start with just explaining the situation we're in. So one thing that we're definitely interested in is the absolute Galois group of Q. Right? This is somehow a very mysterious object, and apart from the identity and complex conjugation, we don't know any of its elements. And Grothendieck had the idea that what we can do is this Galois group naturally acts on certain étale fundamental groups, basically via Grothendieck-Galois theory. And so we get an action of this group on more tractable geometric objects. And in particular, Ihara showed that this gives us an inclusion of the absolute Galois group into the hat profinite completion of Z times the profinite completion of the free group on two generators. And this is something like a very combinatorial object, right? These are just like power series or something. And it turns out that the image of this inclusion actually lands in a group that we call GT hat, which is the profinite version of the Grothendieck-Teichmüller group. And this is defined by explicit equations. So the equations mimic like the axioms of a monoidal category. So you have like a pentagon equation and a hexagon equation and all of these. Later, Drinfeld defined a pro-unipotent version of this group. This is the thing that we're interested in. That, looks similar as just all completions are pro-unipotent now. And he found this he was interested in quasi-triangular quasi-Hopf algebras, which are kind of the Tanaka duals of braided monoidal categories, more or less. And so he found this group acting there. And then finally, Brown showed that just like the normal GT, the profinite one has an inclusion of the absolute Galois group, this has an inclusion of the motivic Galois group. So this is the story that we follow. So the idea is study the motivic Galois group via GT. This is the overarching idea. So what is GT, right? We need somehow a definition. So definitions used to be very equational, but Fresse, I think in 2011, found a very nice characterization, which is you have two operads. The first one is parenthesized braids, and you take the pro-unipotent completion of it. The second one is parenthesized chord diagrams. This is a Hopf operad, so you take group-like elements in here. And these two are isomorphic, but there's a whole set of isomorphisms. These are called associators. And the automorphism group of this operad is GT, and the automorphism of this operad is GRT, which is a graded version of this group. When I say GRT, I just kind of mean any of those. I'm not super careful in this talk about which one I'm doing. And so what is PAB? Well, PAB is the fundamental groupoid of the little two-disk operad. So this is kind of the connection to everything. And as I said, the head just means like the Malchev completion. So this is what this is. It's this automorphism group of braids. And so what do we know about this group? Kontsevich had a very nice paper where he kind of explained the state of the art of this story. And he conjectured in this paper that GRT should act on Hochschild cohomologies. And then in 2015, Dolgoshev, Rogers, and Wilwacher formulated the following theorem, which confirms this. So if X is a smooth complex variety, then GRT acts on the Gerstenhaber algebra of polyvector fields. So we have an action on this thing. It's the hypercohomology of the sheaf polyvector fields of X. And this action is very geometric. It acts by contraction with the odd components of the turn character of the tangent bundle. So this is a very explicit geometric action that we have. And there's a second theorem by Kalak and Vandenberg in 2010, which says that this guy, T poly, is actually isomorphic to the Hochschild cohomology of this scheme. And it turns out that this map is the Hochschild constant Rosenberg map. And then you have to correct for the fact that you want this to be an algebra morphism, just like the flow map. And you have to correct it by the Todd class of X square root. And if you take these two, together, then you get an action of GT on the set of these kind of isomorphisms like this. Because what you can do is you can precompose, GT acts as like automorphisms. So you can precompose and then take the isomorphism, you get a new isomorphism. And this is the only kind of real representation of GT that we know. Everything else is a torsor. So this is the only interesting one somehow that we know. And so what I'm doing is this action, Dolgeshev-Rogers-Villerochas action, is constructed very explicitly. So we have explicit resolutions. We do conservative graph complexes. And so it's very, it's a lot of calculations involved. So what I'm doing is I'm trying to find a more conceptual understanding of why this is happening. So let me write, find conceptual proof of this theorem using operatic homotopy theory and DAG. And the goal of this is find more of these interesting representations, like somehow geometric actions of the Grothendieck-Teichmüller group. By the way, if anybody has questions, please just interrupt me. All right, so I'm going to tell you a bit more concretely what I've been doing in this regard now. And for this, we need a little bit of operad theory. I don't know how everybody is an operad, so I'm going to do a quick recap. So let's see. Be a closed symmetric monoidal category. Then an operad, O in C, is a collection of elements, of objects. We think of these as, n-ary operations that have an Sn action of the symmetric group. And then this is together with equivariant composition maps. So circ, if you have something that has n inputs, and then we take n things, then we get something with all of the inputs of the things that we plug in. So I hope everybody has kind of seen something like this. Let's do some examples. So the easiest one that people take is ASOC, the associative operad. We just have Sn acting on itself. And then maybe even simpler, we have the commutative operad, which is just one operation, point, in each GRT. Cool. What can we do with these operads? So we have algebras over them, right? So an algebra over an operand O is an element in the category together with an operand map from O into the endomorphism operand of A, where this thing has an arity N, just maps from A tensor N to A. And okay, so there's a colored version of operands where there's different types of inputs and outputs, but it's, other than that, it's the same thing. And so for every operand O, there's a new operand, MO, such that algebras over MO are tuples, A comma M, with A an algebra over O, and M a module over A. And when I say module, I mean like an operatic module. So, for example, modules over the associative operand over a given associative algebra, this is, in fact, bimodules, because this is how the operand looks like. All right, so this is kind of a topology-focused seminar, so I have to start pivoting to some topology. So if our ambient category has some kind of homotopy theory, then operands inherit this. So let O be an operand in a, I'm not going to say more, but a well-behaved monoidal model category, then a homotopy O algebra is an algebra over a cofiband replacement. And we usually call these O infinity. That's kind of the standard. And I'm sure you've seen all of this. So we have A infinity, which is homotopy associative algebras. We have L infinity, which is homotopy Lie algebras, and I could probably go on forever. And well, what do we do if we have something that's described model categorically? Well, we make an infinity category out of it. So there's an infinity categorical version. They're called, well, infinity operands. And there's competing ways to encode these. So Lurie has a model. This is the one that we're going to do. But there's also dendroidal sets. And you can do like simplicial operand. So there's other models. And in particular, a topological operand always gives you an infinity operand. Just like simplicial operand always gives you an infinity operand. All right. Let's look at the example that we care about. It's the little K-disk operand. So in classical like 1 or 2 category theory, right, we only have 2 or 3 levels of commutativity. We have associative monoidal categories. We have something in between, braided monoidal categories in 2 category theory. And then we have commutative, symmetric monoidal categories. But there's somehow nothing in between, right? This is just all we got. But if we have a full infinity category, we have infinitely many levels of commutativity. So we have associative, which is not commutative at all. We have commutative, which is commutative. And then we have levels in between. So E2 is the first one that's kind of a little bit commutative. So this is the one that we care about. So what is E2? E2 is an operand that has as its n-ary operations embeddings of n disks, 2 disks into one big 2 disk. So for example, in E2 3, there's an element that looks like this. So say 1, 2, 3, and they all need labelings. So this is one 3-ary operation. And then say this is an element in 2-ary operations. And then say we want to compose them at the first factor. What do we get? Well, we just take all the numbers that aren't involved, and then we take the one that we insert in and insert the second thing into its place. So this is in E2 form. So this is how this operate works. And what we're also going to do during this talk kind of freely is, it doesn't really matter if I take circles or squares, right? It's all circles up to homotopy. And so we sometimes take the model of these squares if it's more convenient, because what you can do with squares is you can take product spaces and get more squares. All right. So what about the little two-disk operate? So first of all, we're gonna pivot from topological to DG. So everything from now on is gonna be DG. You take your topological spaces, take its singular complex, and then you land in chain complexes. Great. So Cohen found the following kind of remarkable theorem, which is that the homology of this little two-disk operate is another operate which is well known, which is the Gerstenhaber operate. So in particular, what this means, if a homology of an operate is another operate, is that if A is an E2 algebra, then the homology of A is a GR algebra. Right? So this is what this means. So what is GR? I'm not sure how much people know about this. The operate GR has two operations, 1 degree 0 product, that is associative and commutative, and a degree 1 Lie bracket that satisfies Jacobi and the Leibniz rule with respect to this product. So it's kind of a mixture of the associative operate and the Lie operate. And so what is the typical example of this? It's surprise, the Hochschild cohomology of an associative algebra. So this is basically the example of a Gerstenhaber algebra. So we have a cup product. It's just a normal cup product, and we have a Gerstenhaber bracket, a kind of degree 1 Lie bracket. These weird operations, they're sums over even weirder operations, where what this thing is F and G are maps from A tensor power something to A. And so what you do is, in the ith slot, you just insert the next function. So it's kind of an operatic type of composition. And so this forms a Gerstenhaber algebra, which is pretty cool. And so we have two pieces of information. Hochschild cohomology is a Gerstenhaber algebra. And if something is an E2 algebra, its homology is a Gerstenhaber algebra. So what's the natural question? Well, it's the thing Deligne conjectured after reviewing this situation, which is there exists a natural action of the E2 operate on Hochschild cochains that lifts this Gerstenhaber structure. Right? So does this arise basically by Cohen's theorem? Is there a lift of this structure? So this is a big question. And it turns out the answer is yes. And we know this for a long time. There's been a whole zoo of proofs. But they all have one thing in common. So they all have the same strategy, which is construct an operate that is equivalent to E2 and that acts more naturally on Hochschild cochains. But the problem with this is that it's kind of inexplicit. You have this different operate. They're usually combinatorial or kind of geometric, and it's not very direct. So what is the conceptual reason we should expect this action, other than Cohen said it would be possible? So conceptual explanation And this was kind of, there's a paper by Hu, Kritz, and Voronov that kind of explores this idea. That is that, well, what Hochschild cochains are basically, I'm going to be careful, are basically the Young-HOM of A as an A bimodule. Right? This is how this arises. It's the ext of A over A tensor A op. And this is a monoidal category with a tensor product taken over A. And in particular, A is the tensor unit. So what happens if we have an endomorphism object of a tensor unit? Well, if we have an endomorphism object of a tensor unit, this always is, like, this is one categorical now, right? So C is a one category. This is always a commutative algebra, right? This is the classical Ekman-Hilton argument. We have two compatible multiplications. One of them is, well, you have F and then you have G, you compose them, you get another morphism from the tensor unit to the tensor unit. And the second one, which is kind of more specialized, is, well, I is isomorphic to I tensor I. And then we can take our two functions, and then we can go back. So this is kind of a convolution. And these two happen to be compatible. And so, well, this thing is a commutative algebra, right? So now the idea is, well, okay, in the infinity setting, can we reproduce this? And the cool thing is that we have somehow an infinity categorical Ekman-Hilton. It's called the Dunn additivity theorem, which was kind of proven in the quasi-categorical case by Lurie in higher algebra. So understated. Let's see the symmetric monoidal infinity category. The morphism rho from ek times ek prime to ek plus k prime, given by taking products of little squares, right? So you have like a little k square, a little k prime square. Its product is a k plus k prime dimensional square. So this is what this map does. Induces an equivalence of infinity categories between ek plus k prime algebras and ek algebras in the category of ek prime algebras. So this is a statement. And, well, as a corollary, the category of two algebras, and by this I mean, associative algebras in associative algebras, two compatible multiplications, just like the classical Ekman-Hilton, is equivalent to the category of E2 algebras. So this is kind of the infinity categorical version of the previous argument. And so what this means is that instead of showing that Hochschild cochains is an E2 algebra, what we're going to do is we're going to show that it's an E1 algebra in E1 algebra, so two compatible multiplications. And so how are we going to do this? Well, I'm sure everybody that has heard of Hochschild cohomology has also heard the following kind of slogan. The Hochschild cohomology is the derived center of the associative algebra. So this can't, quite be true on the nose. The center isn't a functor, so it's got to be hard to derive it. But somehow there's some truth to that, and I'm going to argue in which precise way this is true. So definition: if C is a monoidal infinity category, then a center of an object is a final object, and we're going to denote it a matrix Z of M of the category L mod C fiber producted with M. So I didn't precisely define this category, so I'm just going to explain it. So L mod is left modules in C, so it's pairs of an algebra in C, an associative algebra in C, and a module over it, but just a left module, not a bimodule. And this fiber product basically says these are, so this category are like algebras in C acting on the object M. This is what this category is. And so the center is a final object acting on M. And in particular, this has a forgetful functor down to, algebras. So in particular, the center is an associative algebra in our category. And this is kind of in line with what we think, right? If you have an associative algebra, its center is going to be a commutative algebra. Right. So it turns out we have the following kind of proposition that ties back to who creates Voronov's idea of Hochschild cochains as the derived HOM, which is if A is in the category of O algebras for some operad, then if it exists, the center of A is given by the morphism object of A with A in the categories of operatic modules over A. Right, so this is kind of great because this is exactly how it was in the one categorical case. And so with this, I have proven the following. So if A is an associative algebra, DG algebra maybe, we view it as an object. So there's a theorem that shows how to go from strict DG algebras to associative algebras in the infinity category. So we can view this as an associative algebra in the infinity category of chain complexes. Then the Hochschild complex is indeed a center for A. So in this sense of Lurie. So in fact, Hochschild cochains are the derived center, just we have to derive the category instead of the functor. And in particular, it's an E2 algebra, right? Because the center is an algebra object in the original category, but the original category is, well, associative algebras. So the center is an algebra in algebras in chain complexes, which by Dunn additivity is the same as E2 algebras. So in particular, we do get an E2 action, a direct E2 action on this complex. So are we done? Can we go home, celebrate? Not quite, because there's a part 2 of Deligne's conjecture, which is we want an E2 structure that is a lift of the classical Gerstenhaber algebra structure. So now we have to check this super abstract infinity categorical Lurie style E2 structure we cooked up that this satisfies the cup product and this explicit Lie bracket in homology. So this is the difficulty of this whole procedure. So we have to think a little bit about, if we have an E2 algebra, how do we even get the bracket? What did Cohen do when he proved this? So if we have an E2 algebra, and now we're going to do this one categorically, that's why I'm writing chains on E2. Then in particular, we have this we have this action, right? We have the action of the two area operations on the second tensor power. So it now turns out that E2, 2, so two area operations, as a topological space is homotopy equivalent to S1. So why does this kind of make sense? Well, if I have a circle with two smaller circles and they're labeled, I can take the line that goes through their midpoints. I can orient the line towards the smaller number, and this gives me a point on S1. And this just happens to have a homotopy inverse. So if I take homology, then we get, what's the homology of S1? Well, one component at degree 0, one component at degree 1, and then we get homology of A and homology of A. So this action map yields this action map, right? And so if we distribute this direct sum over the tensor product, we're going to get a degree 0 operation, which is the product. And this yields the bracket. So this is how you get the Gerstenhaber operations and homology out of ED2 algebra. So what does this mean? It means that the product corresponds to the choice of a homology 0 generator of S1, which is a point, right? So I kind of like this point. This is the point I usually choose. And so what does this correspond to in E2 via the homotopy inverse? Well, corresponds to this, right? Two disks that are like on the line. So this is the product. And the bracket is a choice of loop. So the choice of loop that I take is this one, right? This is the classical homology degree 1 generator of S1. So how does this look like in, like, translated to E2 terms? Well, the point P, the start point, right, I just said corresponds to this kind of configuration. So if we walk half, say we walk until the other side, right, then we get just a flipped configuration. And we walked half around the circle, and then we walk the other half, and then we get back to our original point, right? So how does this look like? Well, we kind of move this disk over here, and this disk we move behind. And then we move this disk over here, and we move this behind. This is the path in E2-2 that corresponds to the generator for the bracket, right? So this is kind of the braid that looks like this. And now you can kind of maybe see how you know, the fundamental groupoid of E2 becomes the parenthesized braid operand, you know, because paths in this space will look like braids. So this kind of gives us a roadmap of what we can do, and by tracing through Lurie's Dunn additivity theorem, I was able to prove the following. So if A is in E1 algebra, in E1 algebras and chain complexes, and we call the product, so it has two products, right, up to homotopy, M1 and M2, and interchange law, right? So we have two compatible multiplications. So we have like an interchange law between them, and it looks like this. We have 4 copies of A, 2 copies of A here and 1 here. So here we get the 2 multiplications, and then here we get kind of the tensor products. And here we need the switch in between. So the interchange law now is a 2 simplex in this infinity category. if you have a DG category, it's infinity category, it's DG nerf, has two simplices, you know, the chain homotopies, right? So this is going to be a two simplex given by the two simplex H, which is a chain homotopy. And let H prime be the corresponding homotopy for the opposite multiplications. So associative multiplications have like an opposite, which is like flip the factors in the multiplication. So if we name all of this accordingly, then the bracket in the corresponding E2 algebra structure is given by, okay, this is I have to like do this from paper. So we have H precomposed or whiskered with Yoda 2, 3. So the Yodas are basically, if I have 4 tensor powers of A, right, I can include 2 copies, and the indices just say which copies we include. So we have this plus H prime Yoda 1, 4 plus H prime Yoda 2, 3 plus H Yoda 1, 4 up to higher simplices. So this is only up to homotopy, up to 2 homotopy. Full stop. So this is a theorem, and this is kind of cool, right? We can explicitly kind of give this very low degree in Dunn additivity, and the funny thing is that the way this works is literally write out the most overly complete version of the proof of Ekman-Hilton, the classical one, and then you can translate it step by step. And this will give you this explicit formula. And as a corollary of this, we finally get, yes, this induced E2 algebra structure gives the correct Gersten-Hubbard structure in cohomology. So this proves Deligne's conjecture. And we didn't construct any intermediate operators, and we didn't do braces, and we didn't do anything. And so this is kind of a very nice conceptual way of doing this. And so I started this talk with talking about actions of GRT on Hochschild cohomology of a scheme, right, of something geometric. Until now, we have done algebra, so it's time to globalize this. So now we want to see how the situation looks like if we go from affine to non-affine. And so we're immediately hit with the first kind of hurdle. What do we take as Hochschild cohomology? And kind of, I would say, the most direct thing you would guess is Swan's definition, which is, well, Hochschild cohomology of X is defined as the hyper-Xed of OX times X, and then you pull back OX via the diagonal. Right, so this is the most direct translation of the affine case where we would have Xed A tensor A. This is like the most direct translation of this. The problem of this is no natural Gersten-Hubbard structure. So this guy just doesn't come with a bracket. Like the construction that works in the affine case just doesn't do it. So this is a shortcoming. So for this reason, Kontsevich introduced the following kind of idea. We take the Hochschild cohomology as the hypercohomology of a specific sheaf that he called the sheaf of polydifferential operators on X. So what is that? Well, the poly X on an affine open. This is, well, the poly of A, and the poly of A is a subcomplex of the Hochschild cohomology of A. the Hochschild cochain complex of A. And it's given by maps from A tensor n to A that are differential operators of arbitrary order in each argument. And so this is a subcomplex of the full Hochschild complex, and it actually inherits the Gerstenhaber algebra structure. So the product and the bracket are closed under this property. And so this actually has, so the sheaf dipole is a Gerstenhaber algebra in the derived category. So this is kind of the upshot, is a Gerstenhaber algebra in the derived 1 category of schemes of sheaves of K modules on X. So this fixes the problem of Swan's definition. And it turns out S complexes, they're actually they're the same. Right, so is this kind of done? Well, in my opinion, we should learn from this proof in the affine case that I gave. And I suggest that the most natural thing to take is actually just, well, take the center of OX, full stop. This is its own definition, right? And if you kind of go through the details, this is an element of E1 algebras, in E1 algebras, the derived infinity category of sheaves of K modules, and there's a lot of brackets, I'm going to close too many or too little, of X. So this has, in my opinion, 2 advantages. First of all, it's the exact same definition as in the affine case, which is nice. We don't have to do anything. And it also lifts this Gerstenhaber structure in the derived category, which is basically the structure in homology only. It lifts this to a structure, to the E2 structure in the derived infinity category. So with the full level of coherence. So great. Now I can suggest stuff all day. We kind of have to prove that this is the right thing to take. And so we would like to show that this agrees with polydifferential operators, just like the center agrees with the classical complex in the affine case. And so this theorem, I think it's true, but I haven't written it down yet, so I'm going to put 90% theorem. The sheaf of polydifferential operators on a smooth finite type separated scheme is a center of OX as an E1 algebra in the derived infinity category. Full stop. So once again, this sheaf of polydifferential operator complex actually satisfies the correct universal property. It's final in the category of algebras acting on OX. So what is kind of left is these 2 comparison theorems. They're just for the complexes, right? But there have been previous proofs, classical proofs of the Deligne conjecture, that already equip these classical objects with an E2 structure, right? So we have, I will call them classical E2 structures on dipole. And then we have this center E2 structure that comes from it being a center. And so there's a question of, are these the same structure? Like, do we recover, do we find the same structure just in a nicer way, or do we find like something different? And if we find something different, what does that mean? I very much expect to find the same structure. So work in progress is using formal geometry. So this can mean a lot of things. When I say that, I mean like Gelfand-Fuchs trick. Use formal geometry to show that they agree up to the correct stuff, up to quasi-isomorphism or something. And the way this works is that on formal power series rings, the Hochschild cohomology is formal as a Gerstenhaber algebra, as an E2 algebra. So this means that the complex is quasi-isomorphic to its homology, and this can be basically used to transport and compare these E2 structures. Because they all agree, they all give the classical Gerstenhaber structure and cohomology, right? We showed this. So this is kind of the plan of action. And I expect that we find that they're all the same structure. All right, I think this is it so far. So yeah, if there are any questions, please go ahead.
Thank you very much.